That's weird, right? N squared up there? It's kind of weird. Root test, limit, n goes to infinity. Nth root of this, 1 plus 1 over, 1 over n, to the n, to the n. Tricky. I just did that. Do you see that? What does n squared really mean? N times n, right? And can't I then look at it as being 1 plus 1 over n to the n, and then all of that to the n again? You would multiply these two n's together and get n squared, right? So I'm just being clever in the way I'm writing n squared. What does that allow me to do? Cancel out just one of those, right? And now I have the limit as n goes to infinity of 1 plus 1 over n, still to the n, e. That's e. That's e. We just did that.
So the n that you have on the root over there, that one's always just n?
It's always n.
Okay.
Yep. Yeah, the root test, this is always the nth root. And this is e. And e is bigger than 1, so this, this one. Therefore, it diverges. Okay? All right, we are done, I think. Yes, we are done with chapter 8, section 4. And we're ready to jump into section 5. What's 8.5 called? Power series. Power series. So let's take a little recap of where we are. Okay. Everything we've done, right? We've now established all the tests that we have in this class to determine whether or not a series converges or diverges, right? We have all these tests now, and we are all masters of them. Now, we are going to define a new type of series. Okay, it's a new series. We're going to define something brand new. And what we want to do is pay very close attention to the fact that this new series is now going to contain a variable in it. Every series that we've looked at up to this point in chapter 8, everything we've done, we've had some, right? N equals 1, sometimes it was n equals 0. Then in here we had numbers and we had constants, right? Constants, and we had n in here, right? But we never had some variable x, did we? Now we are. We're going to throw an x in here and you're going to be like, why the hell you can do that? Why you make everything more complicated? Just hang tight, you'll see. So let's define a power series. There it is. That is a power series. A power series is any series that has that form. Please take a special note of what the index starts at. N equals 0 to infinity. C sub n, x to the n. That is a power series. Now, you know how we've been doing these series? And we've had a sub n, right? I've been using a sub n in here. And that was just some formula for a sequence. This right here, this c sub n right here, is exactly what a sub n has been for us in the past. It is just a formula that generates numbers, right? Each one of these, whatever that formula was a formula that created this sequence of numbers, but it just was always a number, right? Number, then another number, then another number, right? And what we're doing is, for this formula we are now adding to it this additional factor. We're multiplying it by x to the power of n. So if you start writing out the terms, you get c sub 0, right? Starting at 0, c sub 0, x to the what? 0. What's x to the 0? 1. So that's just c sub 0. Plus what, c sub, now we're letting n be 1 times x to the 1 plus c sub 2 times x to the second plus c sub 3 times x to the third plus dot, dot, dot forever, right? They call this a power series because it is a series like we've been studying. You have numbers, right? This is a number. This is a number in front of x to the first power. This is a number in front of x squared. This is a number in front of x cubed. This is a power function. They're all powers of x, right? Every single term is a power of x. And so we call it a power series. You could look at it like a polynomial, right? If I stopped right there, what type of polynomial would that be? Quadratic, right? If I went here, cubic, right? If I did just those two, it would be what? Linear, right? Constant, linear, quadratic, cubic, fourth power, right? Fifth, sixth. So you can look at a power series as an infinite polynomial. It's a polynomial that has an infinite degree to it because the degree just keeps getting bigger and bigger and bigger, right? Power series. So like I just said, here the C sub n is the formula that gives us the coefficients of the series. So just like if I were to do, I don't want to give you a specific example yet, but think about this right here. This is what we've been studying, right? That's what we've been studying. This is just a regular old series. Because if you start plugging in values, right? Plug in 1, you get 1/2. Plug in 2, you get 2/3. Plug in 3, you get 3/4, right? Right? That's just a regular old series. If I now add to this x to a power, then I'm going to have powers of x next to each of these. These numbers, right? These numbers right here are basically these things right here, right? So it's all the numbers we used to have with this additional x being raised to powers as you go. And you might ask, why? Why, right? Be patient. So I think I already said this, but no, I didn't say this. So notice that in a power series, we do not know the value of the variable x, right? If x is a variable, then I don't know what x is, do I? I don't. It's a variable, which means what? The convergence or divergence, right, of that series might actually depend on the value of x, right? If I have this series right here, what if I replace all the x's with zeros? What if I say, hey, plug in 0 into this? Can you tell me if this converges or diverges? If I tell you x is 0, then aren't you just adding up like 0 plus 0 plus 0? Does that converge? Yeah, with 0 plus 0 forever. 0, right? So that would be convergent. But if I let x be some other number, it may not converge. So the value of the variable is going to be now what determines if the series converges or diverges. See here, this right here either converges or diverges. Does anyone know what this one does? Oh, that made me real happy if someone could tell me right now if this, real quickly, if this converges or diverges.
I would say diverge.
Diverges, why?
It looks harmonic.
It looks harmonic, yeah, kind of. It's not though, right? Because harmonic is constant over linear. Pregnancy test. Take the limit of that. What do you get? Infinity. L'Hopital. What do you get? 1 over 1. 1. 1 is not 0. The very first test we have, right? The n-term test says if you take the limit of that and you get something other than 0, you have what? You're going to be a parent, right? The test passes, right? You have divergence. So this is a divergent series. Okay? This is divergent. There's no changing that. But if I throw an x next to each of these now the x is going to factor in, right? If x is a certain thing, then it's going to change the value perhaps, or it's going to change the convergence or divergence. Yeah? Okay. So because of that, this is always so, it's so subtle and obvious that it's hard to see. I want you to go back just for a second and think about algebra. If I were to define a function right here for you, okay, forget all series and all that. Just forget it all for a second. If I just put this function on the board right here, what is the domain of this function?
All real numbers except
Everything except 2, right? You can't plug in 2. So domain would be everything except 2? How do you say that? Negative infinity to 2, union 2 to infinity. Right? That's the way to do it with like interval notation, right? It's everything to the left of 2, everything to the right of 2, but just don't include 2, right? That would be the domain. So that means if I plug in any other number, right? If I plug any other number other than 2 in, this thing is defined, isn't it? So if I say, okay, plug in 4, okay, plug in 4, we get 4 over 4 minus for 2, we get 2, right? We plug in 4, we get an answer, right? We plug in 10, we get an answer, right? We plug in negative pi, we get an answer, don't we? Some number, right? The only issue we have is if we try and plug in 2, it's what? Undefined. Okay, that's the idea in college algebra, that if you have a function, right, whatever the domain is, as long as the thing you're plugging in is in the domain, then we're going to have an answer. If it's not in the domain, it's undefined. Well, in a power series, right, let's say that I plug in a value of x and it converges. Then you can look at it as a function. We don't know what it converges to, do we? We just know that it converges to a number. So if I plug in some value of x into here and it converges, then I get some answer, don't I? Plug in some other value of x, let's say that converges, we get an answer. But then we plug in some other value of x and it doesn't converge, it diverges. Then you can look at it like this. The values of x that go in where you get an answer, where we get convergence, would be where the function is defined, and where we get divergence is where we get this situation. And so we can look at this power series as a function. I'm going to illustrate this in the notes some more. So this, if we define this, the only difference in the notation here, all I've done differently is in front of this, I've said, hey, everyone, let's call this f of x. Let's call this a function. And it now depends on x, right? This function only makes sense if it converges, right? This function would only make sense if it converged. Just like this function only makes sense if you plug in things other than 2. This thing would only make sense if the x we plug in gives us convergence. Therefore, the domain of this is all the values of x which make this converge. And so that's what our goal is going to be, is to look at a power series as a function and then to find its domain. In other words, find the values of x which makes it converge. So let's look at our first example of a power series. So the first example we have of a power series I feel like I want to go off on a tangent right now. Let me make up my mind. Let's not. Okay, that's the generic formula for a power series, right? That's the generic formula right there. We're defining a function, a new function, as a generic power series. Now, this C sub n right here can be anything we can come up with, right, that generates numbers. So the very first example we're going to use is the most basic, simple form that we could come up with a formula for that. We're going to say that C sub n equals 1 always. Always, all right? That's about as simple as it could ever be. It's just that you have 1, 1, 1, 1, 1, 1, 1, and then just the powers of x keep going up. So if I let C sub n be this, then we have sum n equals 0 to infinity of 1 times x to the n. Very, very boring generic formula, right? But we're going to start simple. And now let's start plugging in values. So we get 1 times x to the 0 plus 1 times x to the first plus 1 times x squared. You get the idea, right? That is a power series. Written out a little different. 1 plus x squared plus x cubed plus x to the fourth plus dot, 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 dot. And now I need you to squint your eyes for a second. I need to see if you recognize this. Do you remember this? Do you recognize that series? Geometric. This is what a geometric series is. Geometric. If you go back and look in your notes, this is sum n equals 1 to infinity a r to the n minus 1. This is a geometric series. Now, the r here is just some number, right? Some arbitrary number. And the a is some constant. Do you all see that that's exactly what this is? We have here for us ones in front of everything, right? So the a is what? 1, right? The a is 1. And instead of using r's, we're using x's, right? So this is geometric. This is a geometric series. What are the conditions over here? What are the conditions that we have that we need for convergence? What conditions do we have to have for this to converge? The absolute value of r has to be less than 1. For this to converge, right? For this to converge, for convergence, we need the absolute value of r to be less than 1, right? Which means that if this is going to converge, what do we need? So for convergence, we need the absolute value of what? X to be less than 1. Which means that if we define this to be a function, right? If this is a function, f of x, then what is the domain of this function? What's the domain? Well, you can only, this thing will only converge when the absolute value of x is less than 1, right? Which means that if you plug in anything outside of this function doesn't make any sense because it diverges, right? So that means the domain of this, how do you say absolute value of x less than 1 on a number line? What does that look like on a number line? Here's 0, here's 1, right? Anything here works? Not 1 though, right? And then doesn't anything over here work as well? To -1? Absolute value, right, is between -1 and 1. So the domain of this function is -1 to 1. That's your domain as an interval. Because the absolute value has to be less than 1, right? So if pick a number over here, like -1/2. What's the absolute value of that? 1/2? Is that less than 1? Right? So look, anytime we're gonna need this a little bit later this week. Anyway, if you say absolute value of x is, let's say, less than 4, right? What you're saying is that the distance, here's 0. If you go 4 this way and 4 that way, you got to be within 4 of 0. From 0, you have to be 4 to the right or 4 to the left. That's what that means, right? Okay. Quick recap. Generic power series. First example, what if this is very simple, it's just a 1? Well, if it's a 1, then what we get is something that looks like a geometric series. And this thing is defined as long as you are between -1 and 1, then this is true, right? Then this is going to be true. So, what the hell does that mean? Okay, I want to keep going here. Keep going with this idea. So, what I'm saying is this. If the absolute value of x is less than 1, right? If the absolute value of x is less than 1, then the sum as n equals 0 to infinity of x to the n. What that is this formula right here with the 1 right there. I'm not writing the 1 this time. This equals 1 plus x squared plus x cubed plus ... forever will be equal to, drum roll, who can tell me what that's equal to? Let me restate this again. This is a function, right? So if I plug in a certain value of x, it's going to spit out an answer, as long as that x is in the domain. So if I plug an x in between -1 and 1, and I plug it in here, I'm going to get an answer. What is that answer? Well, it's geometric. Geometric series converge if this is less than 1. What does it converge to? What does geometric series converge to? If a geometric series is convergent, what does it converge to? Close? Yeah? What do you? A over 1 minus r. A over 1 minus r is what a geometric series converges to, right? A over 1 minus r. So for us, what's a here? What's r? X. So that should converge to 1 over 1 minus x. 1 minus x. This right here is a over 1 minus r. A for us here is 1, right? And the r is x. So as long as the absolute value of x is less than 1, then this is equal to this. Now, I need you to wrap your head around what we're saying, because this seems like, it should probably seem like crazy to you, all this stuff, just like, what are we doing? You know, like what is the point of all this, right? But look at our conclusion. Our conclusion is that so long as you're only looking in this little window between -1 and 1, there is no difference between this infinite polynomial and that function. If I graph that function and I graph this function, they should be identical on this interval. And if you don't believe me, I'm going to prove it to you. I'm going to graph them. Maybe. Here we go. I got to zoom out. And this is going to be the big, like, point of all of this. I know that's hard to see. I'm going to turn the lights down so everyone can see it. Sorry, I can't make that. I'm trying to make it a little bit bigger, but okay. So what you see right here in red is the graph of 1 over 1 minus x. That's the function on the right-hand side, okay? That's the red graph. And then it's grayed out over here. I just want you to look between -1 and 1. I want you to look at this black curve right here. See that? That black graph? Right now, that graph is the graph of 1. 1 is just the first term. Just the first term, right? Now what I'm going to do is I'm going to graph 1 plus x, the first 2 terms. Here it comes. Here's the first 2 terms. Hey, there it is, 1 plus x. Do you think that the red and black ones are pretty close to each other? Well, that's better than it just was, right? but I would say that they're not very good. Like, they're pretty off from each other, right? Now I'm going to graph 1 plus x squared. Better. 1 plus x squared plus x cubed. Better. 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 Holy shit. Better. 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 Holy shit. Between here and here, the further I go out, the black one is starting to just lay on top of the red one, right? And the further I go out, the better and better and better it gets. And how far do I go? Infinity, right? Which means that for this red function, I have a way of replacing the red function, at least within this window, right? I can replace the red function with the black function. And then you sit there and go, why the would you want to do that, right? Why would you want to do that? Why, right? I mean, why would you ever want to replace this with some big complicated thing like this, right? Well, I agree with you. I would never want to replace this with this, right? I would never want to. But what if I gave you something like this? What if I told you this? And we're going to be out of time here, but what if I tell you this? That this works for any function. So you give me any function. Give me something crazy like, give me f of x equals e to the negative x squared. Give me that function. All right? Well, guess what? This function has already caused us trouble in this class. Like, for example, if I ask you right now to integrate that, find the antiderivative, you can't do it. You cannot do it. Impossible. There's no technique of integration. But what if I tell you that there is a way to rewrite this so that it is equal to something plus something plus something plus something plus something forever? In other words, there is a power series for that function. And now this thing, if you were to go out further and further, if you lay the graph of this out onto this, they lay right on top of each other, okay? Then if you needed to integrate this, you could integrate this instead. And guess what? That integration is going to be easy. Why? These are all just powers of x. These are all just powers of x, right? I still get goosebumps. This blows my mind, okay? Any function can be rewritten in its power series, and then differentiation becomes easy, integration becomes easy, because everything you're differentiating and integrating, each one of these, I mean, imagine this was like 4x to the fifth. Let's say that's what it was. Can you integrate that? You better. And then all of these, right? Now, you have to go forever, don't you? Well, in the real world, we don't need to go forever. Like, there's a certain point where we say, okay, that's enough for building the bridge. We're within a certain tolerance, you know, whether aircraft, ball bearings, something like that. There's still, you know, our machines aren't even precise enough. Have y'all ever seen, I don't know, I'm going off. Okay, but this is the big thing. This is the big thing. There were two fathers of calculus, right? There were the two people who developed calculus because it wasn't known at the time, right? Isaac Newton and, do you all know the other person? Leibniz. That's where we get Leibniz notation from. Those were the two fathers of calculus. There's a lot of historical arguments about how it happened. A lot of people think that Leibniz stole from Newton. We'll never be able to settle it for sure. But the big difference between Leibniz and Newton was that Leibniz did not have series. So Leibniz did not ever develop the idea of series where Newton did. And so Leibniz calculus stopped here. And Newton could just keep going because he had series. And in the real world, right, computer science majors in here, when you type in something like, when you type into your calculator, I have what? 4 minutes. I'm blabbing now because there's not enough time for me to go any further with this. But when you type something like this in to your calculator, cosine of 4, and it spits out an answer, right? What did your calculator do? Does it know your unit, circle, radian? No. What your calculator is doing, it's using the fact that cosine x, excuse me, has a power series. And its power series is exactly this: 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus minus would be next, dot, dot, dot. That is the power series for cosine. And so when you plug in cosine of 4 into your calculator is going 1 minus 4 squared over 2 factorial plus, what, 4 to the 4th over 4 factorial plus, you get the idea? And then it's giving you some decimal answer, right? That decimal answer is just coming from doing that arithmetic. Okay? That's the way a computer works. Computer can do addition, subtraction, multiplication, division, right? It doesn't know that there's a circle and it's all cute, right? No idea. You want to see something really cool? Now, you're just taking this on faith right now. I'm telling you that, right? I'll show you. We're going to be able to do this later. I'll show you how you get this series. But if you can trust me that that's the series, then what's the series for sine? Drum roll. Wouldn't it just be the derivative of that, but change the sign? Right? Because what's the derivative of cosine? Negative sign? So what if I take derivative of this and then change the sign of everything? Let's take derivative. So how do you take derivative of a series? Well, the beauty is that it's just add and subtract. What's derivative of 1? Okay, be careful on this one. Minus, this is 2 factorial, right? That's 2 times 1. Okay, do your power rule. 2 comes out. 2x over 2 times 1. I'll clean it up in a second. Next one, plus this one, 4x cubed over 4 times 3 times 2 times 1. Next one, minus 6x to the 5th over 6 times 5 times 4 times 3 times 2 times 1, right? I'll go one more. Plus 8 x to the 7th over 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Keeps going, right? Now, we need to change the sign, don't we? Right? If we want to know what sine x is, we have to do the negative of this, right? Negative this. So let's change that to a plus. Let's change that to a negative. Let's change that to a plus. Change that to a minus. And let's clean it up now. What happens here? 2's cancel, you just get x. Then you get minus, the 4's cancel, you get x cubed over 3 times 2 times 1, 3 factorial. Plus 6's cancel, x to the 5th over 5 factorial. Next one, see, because the 5 times 4 times 3 times 2. Okay, last one. Minus 8's cancel, x to the 7th over